Okay, so you guys can hear me? Yes? Hello? Hello? I just lost you. Did you say something? Okay. Uh, anyways, welcome everyone. This is fifth class on electromagnetic theory. And if you remember in the last last few classes, we had been discussing about electrostatics, and we spoke about Laplace equations and how to uh, solve for Laplace equations and find electric fields and potentials. And at last, we also spoke about Biot-Savart's law and a bit of magnetostatics, right? So today we'll follow up with magnetostatics. So if you remember in the last class, one second. Yes. So in the last class, we did discuss about this fact that just like static charges give us electric field, if we have steady currents, then that results in magnetic fields. Now, what is steady current? It's basically charges moving, right? So this is something we had seen, that if you have a current carrying wire, and if you say that the current is along, suppose in the vertical Z direction, then we know that it will produce a magnetic field lines and which will be circling around the wire, right? And this is what is called the right hand thumb rule. Now, what was seen interestingly is that if you place two such wires together, what you see is that, so there are two such wires, each with some I current flowing through them. And it was seen that there is a force of attraction, that one wire experiences because of the field that this current carrying wire produces. So this led to this idea that when you have charges moving in an electric field, it experiences some force, right? And that is what gave rise to this idea of magnetic forces. So when you have some charge in electric field, we know that the force is given as Q into E. And now when you have a moving charge in presence of a magnetic field, you have a magnetic force which is given as Q into V cross B. And these two forces together is what gives us the Lorentz force. Okay. Uh, anyone, any question? Okay. Uh, if you have any question, please let me know. Okay. So uh, now one interesting thing about magnetic forces is that, as you can see here, the magnetic forces are always perpendicular to the direction of motion of the charges. It's perpendicular to V, which gives rise to this fact that magnetic forces do no work. Okay. So that means if you have some charge Q moving, we know this is how the force would be. The magnetic force will be given as Q into V cross B. And if you want to find the amount of work done, okay, so if Q moves some distance dl in some time dt, moving with velocity v, that means dl is given as v into dt. So with this, you can find an expression for the work done, which would be given as Q into V cross B dot v dt. And you can see, because the magnetic force is perpendicular to the direction of motion, this work done comes out to be 0. Okay. So it's directed perpendicular to the motion of the charges. Now, if you have a current carrying wire, what you then have actually, so we were talking about this two wires, right? So one wire, this wire, if there's a current here, it would produce some field, right? And because of this presence of this field, you see that the second current carrying wire experiences some force, right? Now, what is this current carrying wire? Basically, it is actually some charges in motion, right? So if you have the current flowing in some particular direction, you can write it as, if you consider that lambda is your, charge per unit length, then, and if the velocity of your charges are given as v, then lambda into v is nothing but your current, right? So that means if you have a current carrying wire, okay, and if you say that now you have some magnetic field, you want to see what is the force on this current carrying wire. How do you do it? So here in this case, your charge will be given as lambda into dl, right? And so basically what you have done here is V cross B. This is this term. And in place of Q, you write it as lambda into dl, and then you do an integration over your entire current carrying wire. Okay. Now, the direction of your current is actually the direction of your, the velocity of your charges. So with that, you can consider that the line element that you have chosen is actually in the same direction as your current. So that gives you this form for your magnetic forces. That is integration of I into dl cross B, where dl is a small element in your current carrying wire, and B is your magnetic field at that position. So integrating over this, you would get the net magnetic uh, force, right? So similarly, this is for a current carrying wire. So in one dimension. Now, if you have something in two dimensions, so if you have a sheet over which current is flowing, then what you define is you have some surface current density. Okay, so then you say if the surface charge density is sigma, then sigma into V will be your surface current density. And then you do the same. Okay, so basically now you say that you take a small section of your sheet. Okay, so dl perpendicular is a small sheet with this length dl perpendicular to the, so as you can see here, this is your flow direction. Flow means velocity direction, and you have taken this length to be a section in the perpendicular direction. So K is given as di by dl. Yes. Yes. Jayanto, do you have any question? Okay.
No, ma'am.
Okay. So basically what we are trying to do is we are trying to write the expression of magnetic forces for different kinds of current distributions. So we saw it for 1D, and now if you do it for 2D, that means you have to take a surface current density. And similarly, this is how your force expression will look like. So initially it was lambda dl. Now in 2D you have sigma dA, and V into sigma will be replaced by K, the surface current density. So similarly, you can have a volume. So if there is a current flowing over a volume, so suppose if you are said that you have a wire and the current is flowing uniformly through the wire. So in that case, what you have is a volume current density. So in that case, you consider such a small, perpendicular volume. Okay. And it's just a extension of what you just discussed. So now you have a volume current density, which is equal to rho into V. Rho is the volume charge density. Okay. And similarly, this is how you define J. And this is how the expressional magnetic force will look like. So based on your question, you have to use these relations to find the force or the charge, the current densities. Okay. So suppose if you have some, wire of some radius A, and there is a current I flowing through the wire, it is asked that it is uniformly distributed over the surface. Okay, so now you have a surface current density. You have to find the surface current density given the fact that it's uniformly distributed. Okay, so how to do that? So the first part will be to find, over what region is your charge flowing, right? So what you then do is, this is your net current. Okay, and K is your surface current density, that is current per unit. If you go back, it's something like this, right? So you have to find this dl perpendicular. So this is a line element perpendicular to your direction of flow of charge, right? So if you have a wire, the current is flowing through the wire, so along the axis. So you have to take the circumference of your wire, which is actually the line element enclosing a surface perpendicular to your direction of flow. So that's why you have here K is equal to I by 2 pi A. 2 pi A is your length perpendicular to flow, which is actually the circumference, right? Now, this is for the case where you have current flowing over surface. If you are said that, if the current is distributed in such a way that the volume current density is inversely proportional to the distance from the axis, what is J? So in this case, again, this is the same setup, but now it's said that the current is over the volume. So you have to find the volume current density. And it is said that the volume current density is inversely proportional to the distance from the axis. What is J, right? So there it said that, so J is proportional to 1 by S. So J is equal to alpha S. Alpha is some constant. And what is the total current? Total current will be nothing but J into dA, right? A surface integral. So here, if you do a surface integral, basically now you are taking a area perpendicular to your direction of flow of current. Okay. And if you do this integration, you will get some expression for your alpha. And then you put this in the expression of J. So this is how you use these conditions and these relations to find the volume current density or the surface current density. Okay. And these are the few relations we just discussed about. Now, talking about force of attractions. So here what we saw that, when you have two wires, the field due to one wire exerts a force on the second wire, right? So if you have two long parallel current carrying wires at some distance d apart, okay, so you would see that, in this case, so if they are here, what is happening is the currents in the two wires, as you can see, they are anti-parallel to each other, right, in opposite directions. And it was seen that currents in this case repel, right? While if you have currents flowing in the same direction, two wires with currents flowing parallel to each other in the same direction, then they attract, right? Now, how to understand this? So what we do is we try to find, so if you take one wire and try to find the magnetic field for this wire, okay, and let us work out the directions, right? So you have two wires, I1 current flowing through one and I2 current flowing through the other at a distance d apart. Now the field due to the first wire at some distance d, and this is the force relation. So now what is the magnetic field for the first wire at a distance d apart will be given as mu0 I1 by 2 pi d, right? And now you have to use this relation to find the force. So for the second wire, your current is given as I2, and you have to do an integration of dl, where dl is some line element in this wire, the second wire, cross B, right? So if you do that, you can see that this is independent of your line element, right? Because it's only a function of how far it is from the first wire. So you can take this out. So basically you do an integration over your length of your second current carrying wire. Now, if you want to find the force per unit length, you would get something like this. So basically you're dividing by the length. Okay. So this is your force per unit length. Now, when in cases where the currents are in the same direction, you can see that the force has a positive magnitude. Okay. So that means it would be an attractive force. While if it is anti-parallel to each other, then what we'll have, you'll have a minus sign here, which would denote that the force is repulsive. Okay. To understand that better, so this is an attractive force. Now we can look at this. So basically you have current carrying, so this is I1, and if you consider that the current is along Z direction, okay, so this is your X, this is your Y, and this is your Z. So your current for the first wire is along plus Z direction. So for this, at some distance d apart, your magnetic field direction will be along minus X. So you can try to work it out using your right hand rule, okay, and you would see that it is along minus X. Now, the dl element that you will choose, so this is for the force on the second wire, right? So you take a line element on the second wire, and the line element will be along Z. So basically, your direction of the force will be given as Z cross minus X, right? And that is equal to minus Y. So minus Y means it's towards the first wire. So it's attractive. Okay. If it was minus I, that is, so in that case, your dl element will be given as minus Z. So then you will have a repulsive force, which will be away from the first wire. Okay. So clear about the directions here? Okay. So I saw some certain questions are pretty standard questions based on this forces, and this is how you have to work out your directions. Okay. Okay. Now it is said that now consider you have two infinite straight line charges. Okay, lambda on like lambda is the unit charge per unit length, and they are moving at some constant velocity v. Okay, and they are at a d distance apart. The question says how great would v have to be in order for the magnetic attraction to balance the electrical repulsion, right? So first point is, so you have two charge distributions and they are moving at some constant velocities. So effectively, what is this about? So when you have some lambda charge per unit length moving at a velocity v, this is effectively equal to a current carrying wire where current is given as lambda into v, right? So similarly, you have another current carrying wire where the currents are parallel to each other, and this is also equal to lambda into v. So for both the wires, the current is given as lambda into v and the distance is d apart. So we know what is the expression for the magnetic force, right? And this would be given as mu 0 by 2 pi d into lambda v, that is the field for the for one wire, into lambda v, that is the current for the second wire, right? So this is your expression for magnetic attraction per unit length. Now the electric field of one wire, so if you go back to your what we had discussed for electrostatics, we know that the electric field for one wire will be given as 1 by 2 pi epsilon naught lambda by s, right? So that means now if you want to find the electric repulsion per unit length, it would be nothing but this into lambda, right? Q into E. So similarly, it would be lambda squared by 2 pi epsilon naught d. So the question says, what is the condition on V? So how fast or how great your velocity should be so that the magnetic attraction balances the electric repulsion. So that means if we have to equate these two terms, we would see that the V has to be equal to the speed of light. Okay. So this is, so you can consider that it's a too much of a speed, right? For a wire. So wires can never get so fast. So that's why it's always the electric force which dominates in our physical world, right? So when we talk about this kind of systems, it's the electric forces which actually dominates. Okay, now let us talk about divergence and curl of B. So initially we remembered about, we spoke about Gauss's law, and we saw that, based on Gauss's law allows us to, simplify our calculations of electrics and magnetic fields, and we can also use the symmetry, which makes things easier. Okay. So now we have a similar thing for magnetostatics as well. So we discussed about Biot-Savart's law, but now just as, just as there was Coulomb's law and then there was Gauss's law for electrostatics, in this case, you'll have Biot-Savart's law for magnetostatics, and the what do I say? The analogous form of Gauss's law for magnetostatics would be Ampere's law. And let us see how to get there. So first is, if you have some current carrying wire, okay, so here you have a straight wire where the current is coming out of the page. Okay, so it's in out of the page. So that means if you use your right hand thumb rule, you know that the magnetic fields will be circling around the wire in this fashion, right? So you can now say that if you want to find the integral of B around some circular path of radius s, how do we do that? So we know that at a distance s from this current carrying wire, your field will be given as mu 0 I by 2 pi s, and then you do an integration over the circumference, right? And this value will be constant, so you can take it out of the integral. And when you do an integration over the circumference, what do you get? You get 2 pi s. So 2 pi s cancels out, and what you get is mu 0 I. So basically, this is mu 0 times I, which is the current enclosed by the circular loop, right? Now, interestingly, what we see is that, so the question is that whether it will it always have to be a circle, and we saw that no, it's not. And let's see mathematically why. So basically, what Ampere's law is that if you have some closed line integral, some closed line which encloses some charge, and then if you do a line integral over this curve enclosing the charge, then closed integral of B dot dl will always be equal to mu naught I, where I is your enclosed current. Okay. And it does not have to be a circular line or anything as such. It can be any loop. Why? Because if you write the general form, so in that case you can use the cylindrical coordinates, and then in that case, because your current is flowing out of the page, so you can consider it along Z. So if you consider it along Z, then your B would be given as mu 0 I by 2 pi s phi cap, right? Phi cap is what is changing along. Basically, you can see the magnetic field lines are circling around the wire. So what is changing is, so it's directed along the phi cap. So now if you take a line element, you will take a line element, which in general the line element for a cylindrical coordinate will look like this. But because your B is along phi, so it's only this term which will make a impact, right? You have to do B dot dl. So all other terms goes to 0. So only S d phi contributes. And now if you do the integration, you'll see that you get mu 0 I. So this tells you that whatever be the integral, whatever be the loop shape, doesn't matter. What matters is what is the charge that is enclosed by the loop. Okay. And now if you use the Stokes law, you can write this line integral in terms of a surface integral. And similarly, you can write mu naught I as mu naught J dot dA, where J is your volume charge density. And then this gives you the differential form of Ampere's law. So while this is your integral form, this is your differential form. Okay. So this is your expression for Ampere's law, which gives us a relation for the curl of B. Okay. This is the integral form. So now you can use the same relation to find the charge for an infinite wire, and you'll see that you'll get the same result as we had got for the Biot-Savart's law. So when we use Biot-Savart's law, it was quite lengthy process. You have to do the integral. In this case, you don't have to do the complete integral considering all the distances and everything. You can directly use the symmetry. So you consider an Amperian loop at some distance S. So that means B dot dl will be nothing but B into 2 pi S. And the enclosed current is I. So it is equal to mu naught I. And this gives you the net field for an infinite wire. Now, let us use this relations, or let us use the Ampere's law to find the magnetic field of an infinite uniform surface current K. So K is given as K into X cap, right? So it's directed along the X direction, flowing over the XY plane. So in the XY plane, the surface current density is along X. Okay. It is asked what is the field because of this current sheet, right? So can you tell me how to proceed with it? So as you can see, there is an Amperian loop, right? So we have considered an Amperian loop. Now, how should the Ampere's law be applied to this? Can you tell me what would be the once you do B dot dl, what do you get? Any idea, guys? So it's similar to, if it is analogous to how we had done for a charge sheet. Like we solved for there were two charge, sigma, minus sigma, and all those kind of questions, right? So it's a similar kind of case, but now it's for it's a magnetostatics problem, right? Okay, so let's see. So first is that, so this is your Amperian loop, right? So you have to do a line integral over this loop, and your K is directed in this direction. So what you do is you do B dot dl. Now here, because your current is, your surface current density is in this direction, you can see this parts will not contribute. This is perpendicular, right? So that means what you will have is one line integral, like this part will be a non-zero term and this will be a non-zero term, the horizontal lines. So basically you have 2bl, and that is equal to mu naught I, right? Because I would be the current that is enclosed by this loop. And what would be I? I will be equal to K into L, right? K is your Kx cap. So K is your surface current density. So K into L will give you the net current that is enclosed by this Amperian loop. So that gives you now B is equal to mu naught K by 2, right? Now, how do we get an idea about the directions? So you can consider that, see, K is directed in the positive X direction, right? So try to, work it out along with me. So if you have your magnetic field lines in this direction, right, in the X direction, so you can consider that for a point which is below the sheet, right? You have your point, if you use the right hand thumb rule, you would see that it's pointing in this direction, right? So it's in the positive Y direction, right? So below the sheet, you have your magnetic field lines along positive Y direction. And then when it circles back up, right? So you will have your field lines in the, so if this is your, it's along X, so you will have a, counterclockwise field lines going about this lines, right? So that means anywhere above the sheet, you will have the fields along minus Y cap, right? And interestingly, the field is independent of the distance from the plane. And this is similar to what happened for a sheet with a uniform surface charge sigma, right? For electric fields. So this is an analogous question to that. So is this clear how we got to this expression of magnetic field? Because this will be quite useful in, so later there'll be questions where you have similar, suppose you have two such sheets and you are asked to find how the magnetic fields will be in between the sheets, outside the first sheet, outside the second sheet, and all those kind of questions. So you have to use this relations that we are currently working on. So is it clear till now?
It's clear, ma'am.
Okay.
It's clear.
Okay. So now, we'll let us see how this will be used for solving numericals. Okay. Now let us move on to magnetic field for a long solenoid. Okay. So consider a very long solenoid with some n closely wound turns per unit length. Okay. And radius is r, carrying some steady current I. So basically what you have is something like this. So you have number of windings along a cylinder. So that means ideally, like effectively, this is nothing but having a surface current density given by K, where K is actually given as how many turns you have and how much length. So if you have n such turns per unit length, so in that case, what you have is, okay, so here they are, I'll discuss about this in details, but basically what you have to first find out is that this is effectively having some surface current density. Now what here we are first talking about is the direction of the field. Okay, so how the field should be directed. So because you have currents in a circular fashion, so you can expect that the field should be in the axial direction. So it should not have a radial component. So here the justifications are given. So it says that if you have a radial component, what would mean is that, so for some current, suppose if you have had a radial component, that means if you reverse the current direction, your field direction should reverse. But ideally, reversing the current direction is nothing but, just turning the solenoid upside down. And turning the solenoid upside down should not change the field, right? So that tells you that you should not have a radial component. And you should not have a circumferential component also, because your current is flowing through the circumferential component, right? Your current is along phi. So your B should not be along phi, right? So your B phi should go to 0, and you can also prove it along by using an Amperian loop, which would show that if you have a B phi component, there'll be no current enclosed, right? Because your current is along the phi direction. So that means now this tells you that your field should be along the axial direction. So that means you will have the BZ kind of component. Okay. So now you use your Amperian loop rule. So you consider such sections. Okay. So if you want to find the field somewhere outside the solenoid, and if you want to find the field somewhere inside the solenoid, you consider two loops. So one is, somewhere a loop which encloses some part of your solenoidal turnings or windings, and this is completely outside the solenoid. Okay. Now for the first case, as you can see, this encloses no current, right? So if you do B dot dl over the line integral, if you do a line integral over this loop, you would see it encloses no current. So that means BA is equal to BB, and that is equal to 0. So basically this part, so this part would contribute nothing, right? So there is no field outside the Amperian, outside the solenoid. But in the second loop, what will happen is, so there is some enclosed current, as you can see. If the number of turns are n per unit length, and if the length is given as L, then the net current that is enclosed is n into L, right? So that means now if you do the integral, you would get B into L is equal to mu naught N I L, right? So that gives you the net magnetic field inside the solenoid. So the magnetic field inside an infinitely long solenoid is given as mu naught Ni, where N is your number of turns per unit length. And you can see that this is a uniform field. But this is for the case where you are considering your solenoid to be an infinitely long one, but in nature, in physical world or in nature, you do not actually have infinite, nothing is infinite. So there will be some finite length, and you'll have some fringe effects and some non-uniformity at the corners. But for an ideal case, this is how your field will look like. And you can see that this is a very useful device for producing strong uniform fields. So if you want to have some electromagnets, this is how you can use it. Okay. Now, I saw some questions on self-inductance of a solenoid. So let us discuss how to get to the expression of a self-inductance and what does it mean actually. So you saw that if you have number of turns per unit length as n, then for some given length, your total number of turns will be n into L. And now there's a magnetic field inside the solenoid, which is given as mu 0 Ni. So that means there'll be a flux of magnetic field lines linked to your solenoid. So if you want to find the flux per unit turn, that is nothing but B into A, right? So you have your field line. So if this is your, what do I say? The cross section of your solenoid, there will be field lines getting into and then coming out of the other side, right? So that means you have to do B into the, what do I say? The so area will be nothing but the circular cross section of your solenoid. Okay. So B into A, where now this is your B. We know it is given as mu 0 Ni and into A. So A is your area for one turn, one circular turn. And if you have n such turns, then the net flux is given as n into phi 1, right? So this is nothing but mu naught n square I A. Okay, so this is length. Mu naught n square L into A, that is your area, into I, that is your current. Now, what is self-inductance is basically the constant of proportionality that relates the flux to your current that is flowing through your coil. So if you have some current flowing through your coil, you say that there'll be a magnetic field line because of that. Now, how is the flux lines related to the applied current that is flowing through the coil, right? This proportionality constant is your self-inductance, okay? So phi is equal to L into I, and if you equate this two term, you get an expression for your self-inductance. Mu naught n square A into L. A is the area of cross section, L is your length, okay? So basically, it depends on the dimensions of your solenoid. Okay, so there are questions. I saw there are questions in the last assignment where you actually have to find self-inductance for a given solenoid where these parameters were provided. So you can directly use this relation to find the self-inductance. Okay. Now let us try to see how magnetic field lines are when you have multiple such coaxial solenoids. Okay, so in this case, you have two solenoids, as you can see, for two different radii, and the currents are flowing in opposite directions to each other. So it is said that this first solenoid with radius A has N1 turns per unit length, and the outer one has radius B and N2 turns per unit length. What is the field in the two, in this three sections? So one is inside the inner solenoid, so that is somewhere here. One is in between the two solenoid turns, and one is outside the bigger solenoid, so outside both. So can you try to solve for this three based on what we had just seen? So for the ideal case, we saw that for a solenoid, the field inside is given as mu 0 Ni and the field outside is given as 0, right? If you have an infinite long one. And here you have to be careful that you have two solenoids, coaxial, and the currents are opposite to each other. So can you tell me what the expression of magnetic field will be when you inside the inner solenoid? Can you try to work it out? So it's important to note that in the first case, so inside, when you talk about inside, you'll have contributions for both the solenoids, right? It's inside both the solenoids. So there'll be a field because of the inner solenoid as well as for the outer solenoid. While outside both, so this third case, it would actually enclose no field lines, right? So here it's outside both the solenoids. So the field outside should obviously go to 0. And somewhere inside, you will actually have contribution of the bigger coil, but you won't have the contribution of the inner coil, right? So can you tell me how the expressions will look like? It's simple, right? So basically, you for the innermost. Okay, is there some chat? Okay. Okay, so somewhere inside you will have, so for one wire it will be mu naught N1I, for the second wire it will be mu naught N2I. Okay, but because they are differently directed, you will have this minus sign, right? Similarly, for the second portion that is between these two, you will not have the contribution of the first one because it's outside. So you'll only have the contribution of the bigger coil. So it would be given as minus mu naught I N2. Right? And anywhere outside, your net field will be going to 0 because it's outside both the solenoids. Okay. Now let us look at another question. And here it says that a large parallel plate capacitor with uniform surface charge sigma on the outer plate and minus sigma on the lower is moving at a constant velocity. Find the magnetic field between the plates and also above and below. Okay. And find the magnetic force per unit area and see what is the velocity v where the magnetic force balances the electric force. Okay. So now if I try to draw, it's basically something like this, right? So you have, it's similar to your capacitor, but now the charges are actually, so your capacitor is now moving with some velocity v, right? So effectively, this is now equal to a sheet with a current, surface current given as sigma into v, and here the surface current is given as minus sigma into v, right? So if we go back to this question where we saw the effect for a single charge sheet, right? And now what you have is two such charge sheet, right? So that means somewhere outside, so if you just recall how we had solved for the capacitor, we saw that inside you would get a field of sigma by epsilon naught, while on the two sides outside the plates, the fields for each other cancelled and we got 0, right? We'll get a similar result here, right? So you can try to solve for it. So basically inside you will have for the first sheet, so the upper sheet, you will have a contribution given as mu naught. So let us go back and just use this formula. So for the first top sheet, inside, so in between the two sheets, so now we are considering the effect for the first sheet. So that means you will have a field of mu naught by 2k, right? And k is equal to sigma by sigma into v, right? And similarly for the second charge, you will also again have a similar field given as mu naught into sigma by v by 2. Now you add the two, so in between the two plates you get the net field to be mu naught sigma into v. While outside, as you can see, for the top plate, the field lines will be directed in the minus y direction, while for the minus sigma plate, it will be directed in the plus direction. And because it's independent of how far we are from the plate, doesn't matter. The direction does not, the distance does not matter. That means the two fields will cancel. So anywhere outside the two plates, the field will go to 0. This is for the case where you have same sigma. Remember this, that in this case, your K or the surface current density for the two plates are the same. That's why they are cancelling, right? Cancelling to 0. Otherwise, there'll be some net effect outside the two plates. Okay. And now if you have to find the Lorentz force, it's nothing but integration of K cross B dA. So you know what K is. K is sigma into V. Okay. And the magnetic field of the lower plate, if you just consider the lower plate, will be given at mu naught sigma V by 2. And so you can find the net force. So this is the force on the upper plate because of the lower plate. And then it's similar to how we had done the last question. So if you try to equate it to the electric force, you would again see that the velocity has to match with the speed of light. Okay. So is it clear how we tried to get to this magnetic field expression? Basically, you're putting K as sigma V and then trying to look at what are the directions of the fields for both the plates. Okay, so be careful about the directions. If you have any doubt, please let me know. Okay. So now if you compare magnetostatics and electrostatics, we see that for this case, for the electrostatics, you have Gauss's law, and then which gives divergence of E equal to rho by epsilon naught, and the curl of E is 0. And then you have for magnetostatics, you have divergence of B going to 0, and this is nothing but hinting at the fact that there is no monopole, no magnetic monopoles exist. And then here you have Ampere's law, which is given as curl of B equal to mu naught J. Okay. An interesting thing about this term is that, so this tells you that if you say curl of B is equal to mu naught J, that means this specifies what your curl should be, right? It has no control over. So if you have a vector potential which is given by this term here. So suppose you define something as a vector potential A, where B is given as curl of A, then you can write curl of B as curl of A, right? And this is the normal vector calculus formula. So this is what you get. Now this law tells us about the curl of your magnetic field lines. It has no control, or it does not tell us about the divergence. Okay. So that means now you have the liberty of choosing the divergence of your vector potential. So basically, if I first talk about electrostatics, we saw that because curl of E is 0, we saw you can write electric field as minus divergence gradient of V, right? And here V was some scalar potential. And in this case, if you add any constant term to it, it does not change the electric field. So that means you have the liberty of adding constant terms or constant scalars to your potential, right? Now, similarly here, if you add something, okay, if you add some constant term such that the curl goes to 0, such that the curl vanishes, in that case, it would have no effect on the B. So you have the liberty of adding any term like this. So if you add a gradient of some scalar quantity to it, because curl of gradient of a scalar would go to 0, that means your magnetic field will still be the same. So you have the liberty of choosing your uh, vector potential. Okay. So you can choose a vector potential such that your divergence of A goes to 0. Okay. So initially, if you have some, A naught, which is not divergenceless, you can add a gradient of lambda to it to make the divergence of your vector potential go to 0. And if you do that, that means this term will go away. And what will be left is, where is this thing? 1 second. So what will be left is divergence del square A equal to minus mu naught J, right? So this is what you will get, del square A equal to minus mu naught J. And now that means you can write an expression of A, that is your vector potential, in terms of your surface current density, volume current density. And this is how it will look like. In case of a surface, then you will have it as a kdA term. Here you have a d tau, that is a volume integral. Okay. So that means if you know the volume current density, you can use this relation to find your vector potential, and then use this vector potential to find your magnetic field using this expression, right? Okay. Now, this were the normal and the tangential components. So these things become very useful when you talk about boundary conditions, right? So if you remember for the electrostatics, if you had a charge sheet, we saw that the normal components had a discontinuity given as sigma by epsilon naught, while the tangential components were continuous. And we could use this relation to find the surface charge density from the potential, right? Or the electric field, right? Now, similarly, in this case, we'll again use our conditions of divergence and curl to find the boundary conditions. So here, because divergence of B goes to 0, that means if you consider a similar structure, you would see that B above perpendicular will be equal to B below perpendicular. Okay, so that means the normal components in this case are continuous. While now, if you consider tangential components, then you have to consider an Amperian loop, something like this. Okay, and then do the line integral, and you'll see that if there is a surface charge, surface current density, then the tangential components have a discontinuity, which is given as mu naught k. Okay, so B above minus B below is given as mu naught k cross n cap. So this is the boundary condition. This is how the normal and the tangential components of magnetic field will look like when you have a charge sheet. Okay. So okay, now so basically now we are discussing all the individual concepts. So later, when we solve, I think there are this kind of questions of sheets, just like we solve for that mu naught k by 2 problem. So we'll have similar problems, and there also we'll see that this boundary conditions will always be valid. Okay. Now talking about field due to magnetic dipole. So the first point is, just as we have an electric dipole where you have, a plus q minus q charge separated by a very small distance. So you say that q into d is actually your dipole moment. So similarly for the magnetic systems, you have magnetic dipoles. Okay. So it says that, actually any small current carrying loop can be considered as a magnetic dipole. Okay. And how do you find the effect of a magnetic dipole, or what would be the magnetic field for a dipole? So you can start with your well-known Biot-Savart's law, okay, and you can try to solve it, but that would be very cumbersome. So what we'll start with is the vector potential. So we'll try to first find an expression for the vector potential. So if we look back, this was our vector potential expression, right? So now if you have a current carrying loop, okay, so you can say that it will be given as your current into the line element, right? So we'll do something like this. So basically, this is what we are trying to do. Now in this line element, you can consider small line elements dl prime, okay, and then consider individual distances from this line element to your field point. Okay, and there you use your vector calculus to write an expression for r. So r is this distance from the line element, current line element to your field point, and this is given by root over r square plus r prime square minus 2 r prime cos theta, where r is your position of your current element, and r prime is your position of a current element, and r is your position of the field point. Okay, so if you do that, you can basically write this as a series of Legendre polynomials. Okay, so that means now what you get is you get the vector potential in terms of a series which includes Legendre polynomials. Okay, and if you look at individual Legendre polynomial terms, you would see that the first term is the monopole term, the second term is the dipole, and similarly, right? So the first term always goes to 0, which again hints at the fact that the magnetic monopoles do not exist. Okay, and this also leads to the fact that your divergence of B goes to 0. Okay. But now if you just look at the next non-zero term, which is the dipole term, then you would see that you can write the dipole. Basically, these are vector calculus. So you can try to write, so r prime cos theta prime is nothing but r cap dot r, right? Basically, you are taking the projection along the r prime direction. So, and then you can, rewrite it such that you get this simplified form. And this is what is important, because this is the useful form. So here you say that the A dipole, this is the vector potential for a dipole is given as mu naught by 4 pi m. M is your magnetic dipole moment cross r cap by r square. Now, how do you define M? So for any current carrying loop, if I is the current carrying loop and D an area, so if you take a small area element and do an integration, so basically the entire area, okay, the area enclosed by the loop. So I into A gives you the magnetic dipole moment for your current loop. Okay, and now you can use this relation to find the magnetic field for your dipole. Nothing but doing curl of A, and this is how it will look like. So this tells you if you have a dipole at different directions from your dipole, how the magnetic field should look like. Okay, and it's important to note that because monopoles do not exist, magnetic dipole moment is independent of the choice of origin. Okay, so whatever origin you choose, the values do not change. Okay, so now let us try to solve for this question. So here you say that you have a net magnetic moment, okay, M, and so this is in the spherical coordinates, and you have r, theta, and phi to specify your positions. It is said that the B dipole looks like this, right? So theta is given by the angle from the Z, and phi is the angle in the xy plane. Okay. So now, if this is how the magnetic field lines look like, you can use this relation to find fields at different points. So there could be questions where suppose you are said that you know the field at this point, okay, and you want to find the field at some other point. Then you have to use this relation, okay. So let us look at an example. So for suppose if you have this position and you say that at this point A, what would be the field like, right? So for this point, as you can see here, the phi goes to 0. It's along x, so phi is 0 and theta is 90. So that means if you put the expression, put the values here, you would get an expression for the magnetic field. It is given as mu naught m by 4 pi d1 cube theta cap. Okay, so it's along theta. Similarly, now for point B, you can again see that here what will happen, your phi will again become 90 here, right? So phi is 90, theta is 0, and B is given by this relation. Okay. So suppose if in your question, you know the field at A and you are asked to find the field at B, you can do it, right? So you have to use this relation. Suppose you know this coordinates. So you know what is your M, and then use the same M to find the field at some different position, right? So I think there was, and in this case, this is in theta cap. So you can use this relations to go to, so this is something which we had discussed long back in our first class, right? How we go from curvilinear coordinates to rectangular coordinate system. So this is in theta cap. So you can use these expressions to go to your I cap, j cap, k cap, basically, right? So there was a question like this in the last year's assignment, which said that you know uh, a small magnet. So a small magnet can be considered as a magnetic dipole. So a small magnet is placed at the origin, and it says that it produces a minus z milliweber per meter square field at this location, right? So basically something like this. Now, what would be the field at some different location, which is given at some point B, right? So can you try to solve this question and tell me what the answer should be like based on what we just discussed? Just try to work it out. So for this question, your D1 is given as 10, right? And your magnetic field B is given as minus 1 Z cap. So if you first try to write this expression in terms of x cap, y cap, z cap, how will it look like? Try to put the value of theta and phi and write the magnetic field expression for point A and B in terms of x cap, y cap, and z cap. Okay. And then try to solve this. Just try to work it out, guys. And tell me if you are stuck somewhere. I think you might get similar questions in your current assignment. So I think this will be useful. So just try to work it out. It's simple, right? Like, are you guys stuck somewhere? If you're stuck, you can write in the chat box or you can also ask me. So for here, when you change it to, from theta cap, if you want to change to x cap, y cap, z cap, try to put, so here what will happen is your, theta is 90, right? So the x cap component will go away, the y cap component will go away. So what will remain is minus z cap, right? So this is nothing but mu naught m by 4 pi d1 cube minus z cap, right? Now that means for your given question, what is given is mu naught m by 4 pi 10 cube is equal to 1, right? And you are asked to find what is the value of mu naught m by 4 pi 3 cube, right? So now I think it should be solvable. Guys, I'd like to have some participation. If you are really stuck or any confusion. Yeah.
Yes, ma'am, it's done.
Done, right? Yes, very good. So basically, these are simple kinds of questions which can come. So just, try to work out these formulas based on what are the coordinates. Okay. And then based on your given information, use one to find m and then use the same m for the next part. Okay. For this case, it will be nothing but something like 10 cube by 3 cube, something like that, right? Okay. Now talking about magnetic fields in matter. So just like in the last, in case of electrostatics, you saw that, if you put some atom, okay, so if you put an atom in an electric field, you know that it gets polarized, and you can have a net polarization per unit volume. So similarly, now you can also have a net magnetization per unit volume. Okay, so it's basically magnetic dipole moment per unit volume, which is called magnetization, right? Now, based on different kinds of materials, you can get different kinds of magnetic properties. So one is a diamagnetic material. So here what happens is when there is no external magnetic field, there is no net field in the material. But when you apply a magnetic field, the moments try to align in the opposite direction. So this is a diamagnetic material. And for diamagnetic materials, you can see if you look at the field lines, disperse away when you are inside a diamagnetic material. So basically here the the mu r is much smaller than 1. So the field strength inside a diamagnetic material is always less than what is the applied field. Okay. Now, similarly, there could be other materials like a paramagnetic material where initially when there is no magnetic field, there is no net magnetization. But once you apply a magnetic field, it has a net magnetization. So in this case, inside the paramagnetic material, there'll be some, so the field lines do come closer and you have mu r greater than 1, right? While if you have a ferromagnetic material, basically ferromagnetic materials do have a magnetization even when there is no externally applied magnetic field. Okay, so at some h equal to 0, h here means, the field that you are applying externally. So when h is equal to 0, you can see that even then there is a net magnetic moment. Okay, while when there is an applied external magnetic field, the moments try to align in that direction. So in this case, when you have a ferromagnetic material, in this case, the field lines come, intensely dense as you have, if you put a ferromagnetic material in applied magnetic field region. So you can see that the field lines come closer. So here inside the ferromagnetic material, the field strength is much larger. So mu r is much, much greater than 1. Okay. So now, because materials can have a net magnetization, that means if you know the vector potential for a dipole moment, you can also write a vector potential for a magnetized object. So if you say that the dipole moment per unit volume is given as capital M, and then if you do an integration over your volume element, what you would get is a net vector potential for your magnetized object. Okay. And if you simplify this term, so these are very analogous to what we had done for the electrostatics questions. So here, if you do this, you can rewrite this in a much simpler format, and you would see that this is using your vector calculus relations, and you would see that the interesting part is you get these two terms. Now the first term, as you can see, has a volume integral, and the second term has a surface integral. So the first volume integral, so you can actually consider this curl of M, where M is your magnetization, as some volume current. Okay. So this is a volume current which comes out of magnetization. Okay. And similarly, you have a surface current which is given as M cross N cap, which is a surface current. So that means when you have a magnetized object, you basically have an effect of these two currents. One is a volume current and another is a surface current. And if you consider the effects of these two currents, you would get the effect of your net magnetized object. Okay. And this currents are actually bound currents which arise because of magnetization inside your object. So it's not what you freely apply in externally. It's a property of your material. Okay. And it's similar to how you had bound volume charge and surface charge in case of electrostatics. So that means now when you write the Ampere's law for magnetized materials, you have to consider the effect of your free volume charge density, and you also have to volume current density, and also the bound current density. So if you consider include the bound volume current density, okay, so then you have it as curl of M. So that it's basically now including the magnetization of your material. Okay. And this is just rearranging the terms. So in that case, you get this relation where your H is called the auxiliary field, which is actually the field that excuse me, that you apply. So H is related to the external field or the free field that you get, while B is the total field. Okay. And B has a contribution of your external field as well as the magnetization that comes in the object. Okay.
Ma'am,
so that means you can
pardon,
write yes.
Pardon, ma'am. Please
Yes,
explain how we can write JB equal to del cross M.
How we can write JB as del cross M. Okay.
Current density
So basically,
JB.
yes. So basically, when we first talked about field of a magnetized object, okay. So here, if you write the expression for the vector potential, you get this integral, right? So you have, for a normal dipole, you have M cross R cap by R square. And then when you have some magnetization M over a volume, okay, then you do this volume integral. Now you can rearrange this term. So basically, you're writing R cap by R square as del 1 by R. Okay. And now you can rearrange these terms further to get these two terms. Now the first term, as you can see, is nothing but mu 0 by 4 pi integration of something over a volume by R, right? So this term, this curl of M that you get here, is the volume current that arises because of the magnetic you can say property of your material. It's the magnetization of the material that results in this contribution in the magnetic field. Okay. So this is this curl of M. So JB is curl of M, which comes from this term here. Similarly, you also have a surface current term, right? So it's the two effects. So ideally, if you have some magnetized material, if you know the magnetization, you can write the field due to this magnetized material in terms of these two currents. Okay, one is the volume current, another is the surface current. So this is this curl of M that you finally use here in the expression of your Ampere's law for magnetized materials. Is this clear?
Ma'am, not too much.
Okay, so can you tell me where you are particularly which portion you're stuck?
How we write this term?
How you get to this term?
Yeah, ma'am.
So basically, it's some what do I say? This is uh, a formula. So it's basically some vector cross gradient of some scalar, right? 1 by r is
Ma'am,
a scalar.
that formula I know, but how
Yes.
we how actually I also get problem when I explain this thing to the among students, and how we can
Okay.
justify them that we can write it.
So what I feel is a way of justification is that similar to what we had initially thought of, right? In case of in case of bound charges, we have a similar concepts where you say that the charges redistribute. The charges redistribute in such a way that in presence of an applied electric field, the charges redistribute in such a way that you have a net volume charge, right? Which is given by something like minus divergence of P, where P is the dipole moment per unit volume. So similarly, in case of a material where you can consider the material to have some magnetic property, that means the material has some current carrying loops inside, right? So in this material, if you say that this material has some magnetization, that means there are certain small current carrying loops inside this material. So now each of this current carrying loops will have a net magnetic moment. Now when you apply an external magnetic field, this magnetic moment will experience some force, and it will try to orient and rearrange in such a way that tries to be the most, the most favorable condition of the medium, of the material. So that this redistribution results in a net uh, magnetization, and that magnetization is nothing but an effect of two kinds of currents inside the material. So it's a mathematical representation of what is happening. So you have small magnetic dipoles that rearrange itself in presence of some applied field. Now this rearrangements can be considered as two currents inside your material. uh, so like, am I making some sense?
Okay, ma'am.
Yeah, I'll see if there are other, better ways of explaining, but like uh ideally this is what I feel is what is actually happening now. Like it's a mathematical construct that makes the understanding simpler. I'll see if there are, better explanations which can make it even more clear to everyone. Is it okay for now? I'll see if we can, make a better explanation of it. But this is what I feel is happening, but there may be better ways of explaining it. Okay.
Okay. Okay.
Yeah.
Ma'am, in
Okay.
second
Yes.
page, yes, ma'am, ये expression AR is equal to mu upon 4 pi. Just show the slide, ma'am, please.
Yes. This
Yeah.
one. Yes.
Yeah. Above 6.12, equation number 6.12 say above, here we get the minus sign, and equations in 6.12 we get plus sign. How we do it?
1 second. 1 second. So here you have curl of.
Using product rule 7 gives there is a minus sign in between the expression.
Right. Right.
and in equation 6.12 we get plus sign. Yeah.
But you can see the order of your, the cross product has changed, right? Basically, you had curl of mr by r into d tau, right? And then, so there are more steps involved, okay? Because here you are interchanging, so you can see it's mr cross dA prime, right? So you have changed from a volume integral to a surface integral, right? So it's not just the, it's just not just writing the first term. So here you use your divergence rule, the divergence theorem. You have Stokes theorem and you have divergence theorem, right? So divergence theorem would help you to relate the, so basically something into d tau will be equal to curl of that into dA. You remember the divergence theorem, right? So it's basically changing from the volume integral to a area integral, surface integral. So because of that, there are like there's a step involved here. It's not just directly from here to here.
But
Try to
what
use
the sign?
yes. So
What
you have to, yes, you have to use the relation. You have to use the divergence theorem. And when you use the divergence theorem, there'll be the order of your cross product is changing. So because of that, you have this plus coming in. You can see it's mr cross dA tau, right? Here it was curl of mr. You will have to use the divergence theorem. So that will be this entire term into d tau is equal to curl of this term into dA, right? And then what you have is curl of something, like curl of this term, and then try to expand it, and then that will give rise to this term. It's not directly from here to here. There are steps involved which changes a volume to a current in surface integral.
Okay, ma'am.
Yeah, maybe I'll it's difficult to write all the steps here. I'll try to write it and then show it to you, then you'll understand. Basically, it's not directly here. It's not that just something has changed from here to here. It's this part, volume to surface integral. Use the divergence theorem. I think you'll get it. Otherwise, I can try to write the steps explicitly and show you.
Okay, ma'am.
Yeah. Okay. So now what it means is that you can write the Ampere's law for the free currents that you apply. And this is how it will look like. So this is for your free currents, which you have control over. So when you apply some current to your, your coil systems, this is the free current. But the magnetization that generates is a property of your material. And based on your material, you will have some susceptibility. Okay. So you say that the magnetization is proportional to your applied field. And this proportionality constant is called the magnetic susceptibility. So now if you include this term here, you would see that you can write B is equal to some term into your applied field. Okay. And this term is your permeability, magnetic permeability. And you can write it as mu naught into 1 plus chi m. Okay. And this is, so if you take a ratio of mu by mu naught, that is your relative permeability. Okay. So this mu by mu naught is actually mu r. So if we go back here, we spoke about mu r less than equal to 1, greater than equal to 1, or much greater than 1. So this is the relative permeability, which is nothing but mu by mu naught. Okay. So there could be questions which makes use of this relation. So suppose your susceptibility is given, you are asked to find the susceptibility is given and your applied field is given, you are asked to find the net field. So then you have to use this relation to find mu and then use this relation to find the net field. Okay, so this kind of small numericals can come in your questions. Now, one can use this relation to, so if you in your question you are asked to find H, you are actually asked to find the auxiliary field, which depends on the applied current, okay, the free current. So here it says that a long copper rod of radius r carries a uniformly distributed free current I. So find H inside and outside the rod. So basically now you know what is your free current. You have to find H. So you have to again use the Ampere's law. And there you can consider two loops. So for the first case, somewhere inside, you have to consider a loop with a radius smaller than the radius of your copper rod. While in the other case, you have to consider a bigger one. Okay. So for S smaller than R, you have H into 2 pi S. Basically, you are doing this integral. So H into 2 pi S is equal to I enclosed. And because it's uniformly distributed, that means the current per unit area will be given as I into pi capital R square. And then the current enclosed will be that term into pi S square. Okay. And this gives you the expression of your H or the auxiliary field inside. And you can see it's directed along phi cap. Okay. So it's that means it is a, so you have a current in this uh in in the axial direction. So your field is along the phi cap direction. So somewhere along the circumference of your cross sections. Okay. And outside, obviously, the total current enclosed is I. So H is nothing but I by 2 pi S. Okay. So for any point outside, it is given as I by 2 pi S. And because anywhere outside your magnetization is zero. So in that case, so in situations where you know what your magnetization is, or you know the magnetic property, so you know mu, you can find the net field. Or if the region is free space, there you have no magnetization, so there m goes to zero. So then once you find H, you can use it to find your magnetic field. Okay. And this is how it will look like. Okay. So inside the wire, in this case, you cannot find because you do not know what your M is. In order to find B, you have to know what is M, or you have to know this magnetic properties to find what M would be. Okay. And based on our, the boundary conditions and the normal and the axial components that we had initially discussed, you can write the boundary conditions for how which relates H and M. So basically for magnetic fields, we know that B perpendicular is equal to B below. And now if you use this relation, you can write how the auxiliary fields are related to the magnetization components. Okay. And similarly for the tangential components. So these things will be useful when you talk about boundary valued questions. Now, this is another question, and similar kinds of questions are very common. So here you have two such, current carrying sheets, and K1 and K2 are specified. Okay. And you can see that the K1 and K2 are in two reverse directions. You are asked to find the auxiliary field H for these three sections. Okay. So can you tell me what the values would be? And you can see why we are asked to find the auxiliary field is because that depends on your net applied field. And if you want to find B, that is the net magnetic field, then you have to also make use of your mu, right? Mu is also given in the question. So now if you use it to find the auxiliary magnetic fields, can you tell me what the values would be? So it's similar to, the question that we had discussed with sigma and minus sigma charges moving with velocity v, right? So let us try to solve it. So for the first part, you can see for z less than 0. Okay. So that means below this lower sheet. Okay. So for surface 1, let us see the contribution of surface 1. So for surface 1, you have B1 equal to mu naught K1 by 2 into y cap. So you can understand, right? The current is flowing in this direction. So the magnetic field lines are directed in plus y direction. Okay. Similarly, now for surface 2, this is the top surface. Your B2 is given as mu naught K2 by 2 into minus y cap. Why? Because now your current is flowing in this direction. It's in the minus x direction, right? Your K2 is directed in minus x direction. So if you use the right hand thumb rule, that means if this is your direction, your magnetic field lines are clockwise, right? Clockwise enclosing this arrow. So you can consider that somewhere below the lower plate, your field lines will be directed in the minus y direction, right? So that means the net magnetic field will be given as mu naught by 2 into K1 minus K2, right? And K1 and K2 are, so basically magnitudes here, K1 minus K2, the K1 magnitude minus K2 magnitude. So here it's both are same. So that means outside the net magnetic field should be 0 and H should also be 0, right? Now, similarly for the second region, okay? So for the second part, what will happen for the surface 1, that is this surface, you can see that K1 is directed in plus X direction. That means here, if you try to use the right hand thumb rule, you can see that above the lower surface, that is surface 1, your field lines are directed in the minus Y direction, right? So your B1 is given as mu K1 by 2 into minus Y cap. And for surface 2, because your field line, your K2 is directed in the minus X direction. So it's in minus X direction. That means again, it's a clockwise field lines will be generated. That means somewhere in between, it will be directed again in the minus Y direction, right? So here that means these two field lines are in the same direction. So they add up, right? So here you can write the effective magnetic field as minus mu by 2 into K1 plus K2 Y cap. And there mu is nothing but 5 mu naught, right? You know the value of mu naught, and you know it, so this is nothing but your relative permeability that is coming in, and then you can try to solve it and you would get a value, right? So this is your net magnetic field somewhere inside, okay? And again in the third section, that is Z greater than 3, again what will happen for the first surface, you would see that the magnetic field lines are directed in the minus Y direction, while for the second surface is directed in the plus Y direction. So again here the two fields will cancel and you'll get H equal to 0. If your K1 and K2 was not equal, you would have got a effective field in this 1 and 3 sections as well, right? Because they're equal, it's cancelling out to 0. Is it clear to everyone?
Yes, ma'am.
Okay. Okay, so I think that's it for today. Any particular doubts, please let me know. I'll see if we can, find a better way of, physically understanding why we get to, JB as curl of M, and like physically how to understand that. There might be better explanations. I'll look into it. Anyone else, any doubt?
It's okay, ma'am.
Okay. Okay, so thank you.
Thank you so much, ma'am.
Yeah, thank you.